Hello everyone, welcome back to the Univ Sin Theta. Today, as a part of our series exploring the world of integrated circuits, we'll be continuing with the chapter Transistors from vacuum tubes to modern MOSFETs. If you haven't checked out part 1 yet, the link is available in the end titles and in the description. Let's get started.
Here's a question that often comes up. Why is silicon the star of the show? After all, we have 119 other elements on the periodic table. What makes silicon so special for integrated circuits? The answer lies in a combination of its material properties, availability, and cost effectiveness. First, silicon is a great semiconductor. It has a band gap of about 1.12 eV, which makes it ideal for switching cleanly between the off state and the on state. This is crucial for digital logic, where we want clear, reliable transitions between those two states easily. Second, silicon is everywhere. It's the second most abundant element in the Earth's crust, found in common materials like sand, silicon dioxide. This wide availability keeps raw material costs low and supports mass production at scale. A major reason silicon ICs are so affordable today. But the biggest advantage of silicon is its availability to form silicon dioxide SiO2 directly on its surface through simple thermal oxidation, a high quality insulating layer with 3.9 relative dielectric constant. This natural formation of the gate oxide in MOSFETs eliminated the need for expensive and complex deposition techniques in the early days of IC manufacturing. SiO2 is also extremely stable, provides excellent electrical isolation, and helps reduce leakage currents. Silicon's thermal stability, mature processing technologies, and versatility across various process corners, voltage, temperature, and manufacturing variations have helped it dominate the semiconductor world. Despite some limitations like low electron mobility compared to the materials like gallium arsenide and lower thermal conductivity than silicon carbide. With that being said, other materials do play important roles. For example, gallium arsenide is used in high frequency RF circuits. Silicon carbide is used in high power and high temperature applications like EVs, gallium nitride in RF amplifiers, and 5G technology. Now let's address a fascinating question. Does silicon's atomic size limit how small we can make transistors? Silicon atoms have an approximate atomic radius of 111 picometer or about zero point 0.1 nanometer. But that doesn't mean we can build transistors at that scale. Today's 2 nanometer technology node already pushes silicon near its physical limits. Not because we are down to individual atoms, but because quantum effects like tunneling, leakage, and variability due to atomic scale fluctuations start dominating at these scales. Talking a bit about BJTs versus FETs, two major types of transistors that have shaped the evolution of integrated circuits. Bipolar junction transistors are current control devices. They have three terminals: the emitter, base, and the collector. A small current flowing through the base controls a much larger current between the collector and the emitter. BJTs are known for their high current gain, large transconductance, and excellent frequency response. They offer high electron mobility in the base region and making them great for analog amplification and RF circuits. Field effect transistors, on the other hand, are voltage control devices. In ICs, we mostly use MOSFETs, which have four terminals. The key idea is that the voltage applied to the gate creates an electric field that modulates the conductivity of a channel between the source and the drain. FETs have simpler structures, consume less static power, and are easier to integrate densely on silicon chips. Although BJTs offer high gain and better intrinsic speed in some cases due to higher carrier mobility, MOSFETs dominate in modern ICs, especially for digital applications. Why? Because MOSFETs leak less power. crucial for large-scale integration and battery-powered devices. They scale to smaller nodes, sub-micron, nanometer technologies, and higher input impedance, meaning almost no current flows into the gate, perfect for logic circuits. The basic structure of NMOS and PMOS transistors consists of source and drain region of one doping type, N plus for NMOS and P plus for PMOS, embedded in a substrate of the opposite type, with a gate placed over a thin insulating oxide layer. When a voltage is applied to the gate, it induces charge in the substrate beneath it. In NMOS, a positive gate voltage attracts electrons, forming a conductive N channel between source and the drain, and in PMOS, a negative gate voltage attracts holes to form a P channel. The MOSFET operates in three regions: cutoff, off-state, gate voltage too low, there is no current and no channel. Linear yet triode region. Channel forms, behaves like a voltage controlled resistor and is used in analog switches. Saturation region. Channel pinches off near the drain, constant current used for amplification and digital switching. In short channel MOSFETs, as we scale down to nearly 100 nanometers, velocity saturation occurs. Carriers can't accelerate indefinitely due to scattering, limiting current despite increasing electric fields. Second order effects at nanoscales come into picture at smaller geometries, which is ideal MOSFET behavior breaks down due to several second order effects, body effect or substrate bias effect. The threshold voltage changes when the source and the bulk are at different potentials. This affects how easily the channel forms and complicates circuit design. Channel length modulation. In saturation region, the effective channel length shortens as VDS increases, leading to a slight increase in drain current, like the MOSFET having a small output conductance. Drain-induced barrier lowering, DIBL effect. High drain voltage reduces the threshold voltage, making it easier for current to flow even when it should not. Challenge for leakage control. Hot carrier effect. High energy carriers damage the gate oxide over time, affecting reliability. Gate tunneling or leakage. When oxide thickness shrinks below a few nanometers, electrons can tunnel through the gate oxide, increasing leakage power. Let's talk about some of the modern transistor technologies that power today's advanced processors. Complementary metal oxide semiconductors (CMOS) technology forms the foundation of nearly all modern ICs. It uses both NMOS and PMOS transistors in a complementary way to reduce static power consumption. That is why our devices can do so much while using so little battery. FinFETs, field effect transistors, emerged as we scaled below 22 nanometers. Instead of a flat channel, FinFETs use a thin, fin-shaped silicon body that the gate wraps around on three sides, offering control over the channel and reducing leakage currents. Gate all around GAA transistors take this a step further. The gate fully surrounds the channel, like wrapping a pipe, offering even better electrostatic control and minimizing short channel effects. This architecture is being adopted in nodes below 3 nanometers. Carbon nanotubes, CNT transistors, and graphene transistors are experimental technologies aimed at pushing beyond silicon's limits. CNTs can offer higher carrier mobility and lower power consumption, while graphene promises ultra-fast switching due to its exceptional electron mobility. Though controlling these materials at scale remains a major challenge, these innovations have enabled amazing levels of integration. For example, the NVIDIA RTX 4090 GPU contains almost 76 billion transistors packed into a single chip, operating at incredibly high speeds with low leakage, high reliability, and the versatility to power everything from gaming to AI workloads. But here's the thing. Creating such a chip isn't a single step process. From extracting silicon from sand, designing, simulating, synthesizing, debugging, floor planning, testability checks, PNR, CTC, STA, layout, to wafer fabrication, transistor formation, layering, patterning, doping, interconnect creation, packaging, testing, and finally shipping. Every step must be precise. It's a combined effort of innovators, designers, engineers, manufacturers, machines, and human expertise. Even with the best processes, sometimes errors creep in. Maybe a defect in the silicon, a slight machine misalignment, or a human oversight. Yet, in this highly competitive world of semiconductors, that constant push for perfection drives us towards even better devices. There's always something newer and more advanced on the horizon. And that brings me to a question I've been pondering. What if someday we move beyond MOSFETs entirely? What if we discover or develop a completely new kind of device that doesn't rely on field effect principle at all? Sure, such a shift wouldn't happen overnight. It would take incremental advances. But what could the next step be? Keep wondering. In this next video, we will explore the complete journey of IC manufacturing from raw silicon to the finished chip in a holistic view. See you in the next one.